Okay, so welcome back to our discussion of how the contents of relational tables are represented in operating system files in so-called heap files, and how these files are organized in units of 8 kilobyte blocks or 8 kilobyte pages. We said, and that's a very important takeaway of the last video, disk I/O always moves entire pages, never individual bytes. Let's focus a bit more on why that is the case and why it's actually essential. The answer to this lies in the internals of such a disk drive, of a hard disk drive, for example. What you can see here is a picture of the internals of a typical hard disk drive. Now you can see why we've used this particular badge icon to represent these disk drives. They are comprised of rotating platters, magnetic platters. Actually, there's many of these. You can see 3 of these in this particular device. And these platters are constantly rotating. Across these platters, we can move read and write heads or read and write arms operated by a stepper motor. Here's the stepper motor. These are the read and write arms, and at the end of these arms you find the read and write heads. These will be used to actually navigate the platters to read and write data to these platters. Okay, so actually this is a very fragile setup. So when these platters rotate, there's a cushion of air on which these very tiny read and write heads are floating. It's actually horrible and it's catastrophic if these read and write heads are just above these platters and the platters stop rotating. The cushion of air will be gone and these read write heads will crash into the platters, destroying the contents. That's actually the horror story for every HDD hard disk drive owner, and a sign of how fragile this particular setup is. Let's zoom into this a bit. So this is a schematic of the same situation. You see this array of platters here. They are in constant rotation, as you can see indicated by this circular arrow here. This is a stepper motor holding several of these read-write arms, and at which ends you will find the read-write heads. Okay. So this arrangement is, of course, the reason for the access and the operating characteristics of such a device, of such a hard disk drive device. This is a view from the top of one of these platters. Okay, so this is the center around which they will spin. This is one concentric ring of space on this particular platter. It's called a track. Okay, so once we've navigated with our read-write on top of this particular track, because the platter is rotating, we could read the different portions of this track, and the different portions of this track are called sectors. This would be one sector, a block of data. A block of data, for example, the 8 kilobytes of data that we are storing inside the operating system heap file, and thus inside a page of such a table storage in PostgreSQL. Such a block would reside on such a sector. Maybe as a block would span many sectors, like 2 sectors in this particular drawing. It depends on the configured block size, the capital B that we were introducing in the last video. So let's say 8 kilobytes, a kilobyte block span like 2 sectors. Reading information from such a setup, from such a platter or such tracks, or writing to these platters, involves the following steps. Before we can actually read particular information out of this block, we would have to use the stepper motor to move the array of read-write heads on top of the correct track. So maybe the read-write head is somewhere here at the exterior. We would have to move it, step it, just over this wanted track. That would be the seek operation. If our read-write head is located at this particular spot where my mouse pointer is pointing now, we would have to wait until the desired blocks are rotating under my read-write head. Okay, so we have to wait until the platter has rotated enough so that the blocks are really under the read-write head. I'm indicating here with my mouse pointer. So there is some rotational delay that will occur. Once the wanted blocks are really rotating under our read-write head, we then of course have to initiate the read or write operation and then actually transfer the data, the magnetically stored data from the blocks over the read-write head into the rest of the computer system. So once we've waited for the seek time and the rotational delay, there would also be the transfer time that really scrapes the bits from the blocks that are rotating under our read-write head. So such a hard disk drive design that involves motors, mechanical parts like stepper motors and so on, and thus of course has inertia. Once we've moved the read-write heads, they will probably wobble a bit until they are really stable over one particular wanted track. Only then it would be safe to really initiate read and write operation at this particular point. All of this adds up to quite some substantial delay, substantial access time, as we call it, before we can really perform read-write operations on such a rotating disk. So the access time for a particular wanted block. Let's read a particular block in a particular heap file residing on a track, on a specified platter on my hard disk time. The access time needed to read the information from such a block, the access time T, will be comprised of these three components. We will have to wait for the stepper motor to place the read-write heads over the wanted track. That would be the seek time TS. We then have to wait. We then have to expand rotational delay until the wanted blocks are rotating under our read-write heads. Rotational delay TR. And then we need to scrap the bits out of the block. We have to transfer the data. That would be the TTR, the transfer time. All of these add up to then define the access time, the time we have to wait until we really can access the bits in a particular block. That's quite some time. And for each random block that we want to access, say, let's access this block, then access this block, then access this block. We will always have to wait until the seek has been completed, until the rotational delay has passed, and until we have transferred the particular blocks. That would be random block access. Random access, sometimes here, sometimes there on the platter on the hard disk drive. I think it would be better to have sequential block access, to read information from contiguous physically adjacent blocks on the disk. That would mean that we would seek to one particular track only, so we would have only one seek time to endure. Then we would wait for the rotation to happen, so there would be one rotational delay to access the first block in this contiguous sequence of adjacent blocks. But once seek time has passed and once rotational delay has passed once, we are over the wanted block, can access it. The next wanted block will be in immediate adjacency to that, physically contiguous. So no new seek time, we are on the same track, no rotational delay. The next block is just after the block we have just read, sequential block that's called. So we would have to endure the transfer time because we want to read the bits from these particular blocks, but TS and TR would only hit us once. So reading larger portions of information from such a disk, we better do it in a sequential block access fashion where we read and write multiple blocks that are physically contiguous, adjacent on the same track, say, and really adjacent on that track to save time here. How long these access times really are, that can be checked by looking at the data sheets that come with each hard disk drive that you can buy today. This is the excerpt of a data sheet of a Seagate Cheetah 515K.7 hard disk drive. That's a contemporary drive that I've just picked at random. This is not a particular fast or particular slow drive. It's a regular average consumer hard disk drive. And you can see that it comes with 4 platters with 8 read-write heads. So read-write heads would be located on the top and on the bottom of these platters. On average, in such a concentric ring and in such a track, we would have space to store 512 kilobytes of data. You can imagine that the inner rings will store less data than the outer rings. The overall capacity of the disk will be 600 gigabytes. This would be the rotational speed of the hard disk. So 15,000 revolutions per minute would be the speed in which the platters would rotate. That's quite fast, but still super slow, as we will see. The average seek time, the time we have to invest to let the stepper motor do its work and move the read-write heads, that would be 3.4 milliseconds. But it would only be 0.2 milliseconds if we only need to seek from track to track. Not some arbitrary read-write head movement across the entire platters, but from track to the next adjacent concentric ring to the next track, that would be just 0.2 milliseconds. Once we've expanded all these navigation read-write head operations, we could start reading data, and that would happen at a rate of 163 megabytes per second. Okay, so given this excerpt of the Cheetah data sheet, what would be the random access time T for a single 8 kilobyte block, for such a block in our heap file? Well, so on average, we would probably have to wait half rotation of the platters. So maybe we are lucky in some occasions, and the wanted block just rotates under our read-write heads, so good for us. But in other situations, the wanted block might have just passed us, and we have to wait for a whole rotation until we can read it and see it again. So on average, there will be half a rotation to wait for us. And given this rotational speed, that would mean that we have to wait about 2 milliseconds on average until the wanted block really rotates under our read-write heads. Once it has done this, we can start the transfer. We only want to transfer 8 kilobytes. So if 163 megabytes are transported per second, and we only want to read 8 kilobytes, that would only take us about 0.05 milliseconds. Okay, so now we have all the components. The transfer time for random access of a single 8 kilobyte block would be the seek time, 3.5 milliseconds, 0.4 milliseconds, the rotational delay, the average rotational delay, plus the transfer time, adding up to 5.45 milliseconds until we can read the wanted information. Sounds not too bad, but it is bad. How about sequential block access time? We said that this would be the superior mode of access because we only have to expand the seek time and we have to wait for the rotational delay only once. Then what comes into play is the track-to-track seek time, which is also quite nice, 0.2 milliseconds only. Okay, so let's see, we want to really transfer a larger unit of information in this case, not a single 8 kilobyte block. Let's say we want to transfer 1000 blocks of 8 kilobyte information, so 8 megabytes, about 8 megabytes. If you would do that in the normal random access time fashion, so we would have to expand 1000 times the access time that we have just computed, and that would be 1000 times this particular value, and that would be 5.54 seconds, and that's really super slow. So 5.45 seconds to read these 8 megabytes of data in random access mode is really some waiting time. In sequential mode, the whole thing looks different. and quite a bit better. So the information in these 1000 blocks would not be arbitrarily spread across the platters, but they would be in 1000 physically adjacent blocks. So given that we can store about 512 kilobytes per track, these 1000 blocks would span 16 tracks, 16 concentric rings on our platters. And the overall access time, the sequential access time for these 1000 adjacent blocks of 8 kilobytes would be the following. We would have to wait for the seek to happen once. We would have one rotational delay. We would have 1000 transfer times because we want to read the bits of all of these 1008 kilobyte blocks. And then because all of these blocks don't fit on a single track but would have to distribute it across 16 tracks, there would be some seek to seek, track to track seek time that we have to invest here. But all of this only adds up to 58.6 milliseconds. So that's 100 times faster than the random access mode that we have just considered above here. So whenever we can, and we want to read larger portions of information from such a hard disk drive, try to use sequential access. Read information from physically contiguous adjacent blocks that only need us to invest TS and TR, seek time rotational delay, once. It's actually super bad, and random access time really is forbiddingly slow, and it's even if we only want to read about 1% of any particular file, it's probably better to just read the entire file sequentially than to read random blocks that are distributed across the platter. So sequential access time really wins here. So this is the situation for these hard disks, the rotating platter disks. How about modern drive technology like the solid state disk drives that are really pervasive in computer systems now? And the laptop that's sitting right here on my desk has an SSD built in. That would be the primary means of secondary storage beyond RAM. And what are the access characteristics of such modern SSDs? They don't have any moving electromechanical parts, no motors involved, no inertia involved. It's just a particular type of non-volatile flash memory that has been used. Actually, it's battery-powered DRAM or NAND memory, so that even if my system powers down, it's ensured that data will stay persistent. Accessing such DRAM-like memory, of course, incurs no seek time or no rotational delay. There are no electromechanical parts involved, no motors, no rotation, no platters. So the seek time and the rotational delay are actually absent. There is no such thing. All that we would incur is the transfer time. No motor spin up, no jittering of read-write heads and so on. Perfect. That should actually admit low latency, so very fast random read access. No TS, no TR. We could access data blocks immediately, and typically the block size for such SSDs, the number of bytes that are moved in one read-write operation to and from these SSDs is typically larger than 8 kilobytes. So a typical value would be 128 kilobytes. So initiate a read-write operation with the SSD controller of your system, and you would normally move 128 kilobytes of data from SSD to RAM, or from RAM back to SSD. This looks good to me. So random read should be really fast. It's not all good news, however. Random writes, for example, are much slower in such SSDs. This has particular reason that we will not dive into in this particular course. Group of blocks have to be erased before they can be rewritten again and so on. You can look up the details about the internals of such SSDs if you're interested in that. There's other complicating factors like the memory cells inside such a SSD, the wear out after a particular write cycles. So the SSD has to make sure to spread information evenly across the memory space. But let's not concern with that with these details here. So that would be an excerpt of the data sheet of one particular SSD. Actually, it's the SSD built into this laptop I'm using here, the MacBook Pro. That's NAND flash memory. It has a capacity of 1 terabytes. And the block size, as I told you, 128 kilobytes. That's the unit of information that will be moved to and from the device at a rate of 1.8 gigabytes per second. Oh, this sounds better than the 163 megabytes of transfer rate I had with my Seagate Cheetah. Okay, so what now? What about the random access time for 1000 blocks of 8 kilobytes? Okay, so there would be no seek time and rotational delay. All that we have to endure is the transfer time. We can transport 1.8 gigabytes per second in a second. We only have to move 128 kilobytes. We cannot move less. So that would be 0.06 milliseconds per such a read-write access. We need 1000 of these because they are distributed randomly in memory space on my SSD. So this times 1000 means 60 milliseconds of random access time. Compared to 5.45 seconds for the HDD, that's quite an improvement. Okay. Still, sequential access wins even for these SSDs. If we have to read 1000 adjacent blocks of 8 kilobyte information, and these 8 kilobyte information blocks are really adjacent, so in one of these 128 kilobyte blocks, we really find more than 8 kilobyte worth of information, but the full 128 kilobytes are really information that is valuable to us. And when we read it, we can make use of it. Then the situation is even better. So this is the general amount of information we want to move. This will be accessed in these 128 kilobyte units. Each of these will incur this transfer time, or will be moved by this at this transfer rate. So sequential access time is 3.75 milliseconds only. That's still an order of magnitude better than the random access time. So still sequential access pays off even for these SSD devices. Okay, that's good to know. So these are really nice and very fast times. Why have RAM at all? Why not store everything in SSDs? Is SSDs, are they as fast as RAM already? Because SSDs have no no seek time and no rotational delay. DRAM hasn't either. So these should compare rather directly, right? So let's have a speed comparison. Let's have a speed comparison of the transfer speed of reading and writing information. In this case, writing information of to a SSD as compared to reading or writing information to DRAM, to normal RAM. We could use a simple Unix systems command, for example, for such an experiment. This is the command dd that you see here. Okay. So disk dump. What I do is I will just read a system provided source of zeros, the dev0 file, the virtual file from which I can read an arbitrary amount of zeros. I will output them into a file I call bitbucket, stored in a temporary directory, and I will move 4 gigabytes of such zeros. So 1024 kilobytes of information times 4096 repetition. That makes 4 gigabytes of data written to the file system and thus to the SSD of my particular system. If I do that, I will see that, of course, 4 gigabytes of data will be transferred in 2.8 seconds. That means the transfer rate is about 1.5 gigabytes per second. So this is the transfer rate I can achieve with this particular SSD. The data sheet was promising 1.8 gigabytes per second. Probably this is marketing speak, or my experiment has been I've been unlucky in my experiment, but 1.5 gigabyte per second, that's in the expected ballpark. All right. So how about DRAM transfer speeds? To measure that, let's write a small C program. A small C program that can measure the read and write speed, in this case the write speed of writing information to the RAM, to the primary memory of this particular machine. We will again write 4 gigabytes of data, in this case 64-bit value, 64-bit integers. And how we will do that is by allocating an area in my C program of size 8 megabytes. 8 megabytes has been chosen so that it exceeds the size of the sum of the sizes of all of my CPU caches. So I want to make sure that the write operations I'm making here are not hitting the caches, are exceeding the cache sizes, and are really hitting the RAM. So I'm not measuring cache speed here, but I'm really measuring the RAM speed in my particular experiment. Let's look at the program for a minute. That's a C program. I warned you that you would be exposed to C code in this particular lecture. Now is the first time. You will find this C program also on the GitHub repository for you to experiment with. So that would be the main program here. As you can see, I'm allocating 8 megabytes of memory. Scan size would be a value representing the 8 megabytes. And I'm asserting that I could actually allocate this particular piece of memory. Then I would measure the current time of day, save that in time t0, perform the scanning, the writing of the 4 gigabytes, and then measure the time of day again, and just compute the difference between the two timestamps that I've recorded here to output the duration of the scan operation, the memory write operation here. The memory write operation is in function scan. It's a very simple function. As you can see here in the inner loop, I'm actually writing to this mem pointer, which is just inside our scan area. I'm writing 64 bits in one go. So I'm writing this particular value 42 inside RAM here. And you see that the two nested loops here make sure that I'm actually writing 4 gigabytes of data. So I'm writing into this 8 megabyte area in 64-bit steps. And I do this such that the inner loop is repeated often enough set that I actually write bytes worth of mem size, and mem size is 4 gigabytes, as you can see here. I invite you to have a look at this particular C program. It's very simple. Just go through it bit by bit, and you will see that nothing particularly complicated happens here. Okay, so let's see. We could compile this program. So with optimization. Transfer. Okay, so let's do that. Okay, so and let's execute the program. There you go. Okay, execute again. Execute again. So this is the 306,000 microseconds of time has passed to write 4 gigabytes of data into DRAM, really into primary RAM. You see that I've performed this experiment a bit earlier on. and measured better times at this particular experiment. So looking at this transfer time for 4 gigabytes, it's easy to compute that it's about 15 gigabytes per second. 15 gigabytes per second I've written into DRAM. This is compared to the 1.4 gigabytes per second that I could write to the SSD. So writing to DRAM is still 10 times faster. And I could, of course, write to DRAM even faster if I would use the SIMD instructions of a modern CPU, so write larger chunks of data, or even play other tricks of parallelism, but still the memory bandwidth would limit me there. But 15 gigabytes per second is something that I could achieve here. I brought a different program with me that can measure the actual bandwidth of memory read-write operations. So you can see that our transfer.c program above did not go wrong. So let's do that. Let's let it run for a few seconds. You see that this bandwidth measuring program is writing to DRAM ever larger chunks of data. So we are currently writing 512 kilobytes, 1 megabyte of data, 2 megabytes of data. Okay, let it run for a bit. All right, I think that should suffice. So you can see that first of all, you can see, let me scroll up a bit. First of all, you can see these are the cache sizes of this particular computer. And as you can see, the L3 cache, the largest cache, is of size 4 megabytes. We were writing 8 megabytes to DRAM, so we were clearly exceeding L3 cache size. We were really hitting the RAM here at this particular point. Okay, so looking at the benchmark here, you see that if data sizes are really small, we are hitting the caches in close to the CPU, and we can read and write like 68 gigabytes per second. That's quite a nice rate, given that this computer is currently super busy to record the video I'm currently taking for you. So this has to be taken into account. Okay, when the data sizes get larger, then we will leave the sizes of the caches. So this is the data cache next to the CPU. It has size 32 kilobytes. So if we exceed that, I expect the data transfer rate to drop. So if we still fit in this particular L1 data cache, it's 52 gigabytes per second. If we exceed that only slightly, we are penalized and hitting other caches, slower caches here, and only see a transfer rate of 38 gigabytes per second. And if we move out of the L3 cache and into actual DRAM, we see read and write rates of 8 or 9 gigabytes per second. Given that I'm currently recording video here, it's actually not too bad. So this is comparable to the transfer rates that we have been measuring with our transfer.c program. Okay. So this was about transfer speeds that are really different if we are considering DRAM or SSDs or hard disk drives. Okay, and the differences between these different storage media, the different devices that we can write and read information to and from, are really staggering. These are the transfer speeds. There's another component to consider, and that's the so-called latency. How long do we have to wait until we can write or read the first byte to a particular device? That's the latency, the actual latency. And you can see that if you want to read and write from the L1 cache, which is next to the CPU, that's about 1 nanosecond. That's a rough value at this particular point. So a wait time of about 1 nanosecond before we can actually read or write a byte to the L1 cache. It gets worse if we use the caches that are further apart from the CPU. So it's 2.8 or 28 nanoseconds if we have to hit the L2 or L3 cache in the cache hierarchy. So the latency, the wait times until we really can perform the very first operation, read-write operation, really goes up. It's about 100 nanoseconds, so even it's 100 times worse than hitting a cache if you have to really access RAM. And it's 50 to 150 microseconds or 1 to 10 milliseconds if we actually have to hit one of these secondary disk drive devices, SSDs or HDD. So we had a seek time of 3.4 milliseconds for one of these Cheetah HDD that really falls into the range of 1 to 10 milliseconds here. That makes sense. So the latencies go up very steeply because nobody out there can make sense of nanoseconds, microseconds, or even milliseconds. I've translated that into a scale of time ranges that a human can perceive and understand. So if we would normalize the CPU, the single CPU cycle in our system to last 1 second, of course it only lasts 0.4 nanoseconds, but if we would normalize this to 1 second, then L1 data cache access would last 2 seconds. L1, 2 and L3 cache access would last 7 seconds or 1 minute already. RAM access 4 minutes. SSD and HDD access would be measured in days, weeks and months of waiting time before the first information could be transferred. So really, by designing database systems and the algorithm inside the system, let's make sure that we can read as much information as possible from the caches or at least from RAM. Otherwise, the waiting times that will occur are monstrous. Let's not even look at the internet round-trip time. That really makes me dizzy here. Many design decisions in database systems become a lot clearer if we have this table of latencies, waiting times, and the transfer speeds that we are measuring, if we keep these in mind. Okay, so that concludes our discussion of these transfer speeds and waiting times in the different storage media that our database systems will be operating over. I think that should conclude it for now. Thank you for your attention, and we will continue our exploration of heap files in the upcoming videos. See you then. Bye bye.